Now we're going to try and understand why the arc length is given by this in 3D. So when given your position vector, so that's this particle moving along like this from A, which is this point here, to B, which is this point here. So this arc length here is given by this thing here from A to B. So we're going to try and understand why the arc length is given by this. So the idea here is that I'm going to remind you how we worked out the arc length in the form of y equals f of x. We've done this before, so I'm just going to quickly remind you how we worked out the arc length from one point to another point. And then I'm going to remind you how we worked out the arc length in parametric form when x is given as a function of time and y is given as a function of time. So time's a driver of everything. So I'm going to remind you, and again we've already done this, I'm going to remind you how we worked out the arc length in parametric form, and then combine these two to extend it to 3D. So you've got your x, y, and z. We're going to extend it to 3D, and in 3D, hopefully it will allow us to understand why the arc length is given by this. Okay, so let's start. Hang on. So when you've been given, let's say y equals f of x here, so you've been given a curve in terms of x and y, and the idea here, we did this last time. The idea here is to use Pythagoras to work out this diagonal line here. So we would get dx, we would get dx, square this, and then square dy. So square dx, square dy, and then take the square root of it. So it's us using Pythagoras to work out this diagonal length. And then we would do the same here. We would use Pythagoras here. So your dx here, dy here. Use Pythagoras to work out this diagonal length. And then we would sum up all the diagonal lengths. And then that would be approximately our length. And then later on, we would take the limit as the width here heads towards 0. So we would decrease this width here, so it's heading towards 0. So hang on. So the actual length like this is approximately this thing here. So now remember the mean value theorem. And remember, we've done this before. I'm just reminding you. The mean value theorem. If you get dy divided by dx, that will then give you the average gradient. Well, the mean value theorem says that somewhere along the actual function there exists a c somewhere in between here and here, where the average gradient is equal to the gradient of the actual function. So remember, if you can't remember this, you've got to look it up. So you've got your average gradient here. This is your average gradient. Remember, we did this. Wait there. We did this. We moved it, and right here, hang on, let's start again. So we've got, this is our average gradient here, and then we would move it like this. We would move it like this. Hang on. We would move. Oops, wait there. We would move. Oops, wait there. Well, we will right. You see, at this point here. Bear with me. Bear with me. Yeah, right somewhere around here, right at this point here, there exists a C. There exists a C somewhere between here and here, where the gradient of the actual function is the same as your average gradient. So there exists a C somewhere that equals the average gradient. And if you can't remember this, you've got to backtrack this. It's the mean value theorem. So we can times both sides by this. So every time we see a dy, we can replace it with this thing here, and it will be precisely equal to this thing here. So we would put this block. Remember, if you can't remember this, also try and understand when we first started out with the fundamental theorem of calculus. I asked you to imagine that this is a fish tank, that this here is your fish tank, and then this thing here is water, and I would ask you when the water settles, it will settle somewhere around here. And I would ask you, where will the water settle? Well, it will settle somewhere around here. And the way you would find out would be for you to work out this whole area here. That would be this block here. And then you would divide it by h, which is the width here, divided by h. And then that would tell you where the water will settle. And the water settles somewhere around here. And there exists a C. There exists a C somewhere between A and B, such that this whole thing here is precisely equal to, well, to you putting the C into this function here. And we've did this before, so if you don't remember, backtrack. Well, anyway, the mean value theorem is this thing here, and then we'll times both sides by dx. That will then give us this thing here. So now we can put this whole block into this delta y. So that will then take us to here. So here you've got one block multiplying another block, and then the whole thing squared. So you can tidy this up. Hang on, because what's in common is this block here, delta x squared, and then you've got delta x squared. You can actually factor out the delta x squared. So if you get this times 1, that will then give you this. If you get this thing times this thing here, that will then give you this. So from here, that will then take us to here. So remember, the arc length is approximately the arc length is approximately us summing up all these diagonal lengths. It's approximately us summing up all these diagonal lengths. So down here, the arc length is us summing up all the diagonal lengths. So tidy this up. That will then take us to here. And then remember, square root of a times this thing here is equal to root a times root b. So we can break this up as one thing, and then break this up as another thing. So that will then take us to here, and then tidy this up. That will then become this, and then so the arc length is approximately this thing here. So now take the limit as n. Remember, n is like the number of strips. So hang on, going back to here, n is like the number of strips. N is like the number of strips. This is 1, 2, 3, 4, 5, and so on. So as n tends to infinity, you can see that this width here heads towards 0 because you're going to have more and more strips. So when n tends to infinity, the width here tends to 0. Just bear that in mind. Hang on. So going back to here, the arc length is approximately us summing up all the diagonal lengths. Now take the limits as n tends to infinity. Well, n is the number of strips. So as the number of strips increases, the width of the width. Let's say you've got your function here. The width decreases. The width decreases. So as the width decreases, remember there exists a c somewhere between here and here. So as the width decreases, the c will lie on top of the function itself. So this c here will lie on top of the function itself. Well, here it's a derivative of the function. So as you take n, as the number of strips tends to infinity, the width decreases. Well, this c being somewhere in between this bit and this bit will just lie on top of the derivative of the function, which this thing here will then become this. Now we've done this many times, so if you don't understand this, backtrack to one of the earlier videos. So this is approximately us summing up all the diagonal lengths. But then the minute you take the limit as n tends to infinity, it becomes precisely, the arc length becomes precisely this whole thing here. Well, when you take the limits as n tends to infinity, you summing up each diagonal thing is the same as you taking the integral of the whole lot. So hopefully, remember, this is just a reminder. You should already know this by now. So the arc length is given by this. In the next video, we will look at it in parametric form, and then we can extend it to 3D. Okay.